Measured A is the black dot. Fitting a model projects this down onto the BC plane. That's shown as the dark line connecting the black dot to the open circle. This is the residual vector. The residual is always exactly perpendicular to the plane. That's the nature of the least squares fitting process. But the random factors, the red line that connects the deterministic A and the measured A, need not be perpendicular to the plane. This is most evident for small sample sizes. So try setting the sample size n to n equals 2. Generate several new random samples. By and large, the random factors won't be perpendicular to B and C. But for large n, try n equals 100, the statistics of randomness result in the random factors being almost always close to perpendicular to B and C. The overall result is that for large sample size n, the projected version of measured A tends to be closer to the deterministic A than is the case for small sample sizes. Now to construct a sampling distribution. We have an estimate of the length of the red random component. Of course, we don't measure the red random component directly, but the residual vector gives us a good idea of how long it is. Imagine adding a new random vector to the measured A and then projecting this down onto the BC plane. That would give us a good idea of how far the deterministic A is from the model values. We don't know what direction the deterministic A is in, but by making lots of such samples, we can be confident that we'll cover it. That's the job of the confidence interval. Click on the Show CI simulation, and you'll see many such random vectors and their projection back onto the BC plane. That gives an idea of how the confidence interval is calculated.